Now, today we're going to do probably the most common type of calculation there is. And most of you are familiar with something called a combination. Now, last week we did permutations. Permutations are when I'm ordering distinct objects, how many ways can I put them in order? And so that we came up with a simple formula. But the question is, what if I don't need to put them in order? You see, I'm going to form the first ever discrete math basketball team. And so 5 of you are going to be on my team. So if I pick Cynthia on the team, does it really matter if she's the first, second, third, fourth, or fifth pick? Does that make any difference where she's picked? Or is it just that she's on the team? So if I'm picking and Jesus is the 3rd pick, is that different than if Jesus was the 2nd pick or the 4th pick? No, he's on the team or he's not on the team. It's actually a fairly simple notion. If I said I'm going to have a race in 1st, 2nd, 3rd, 4th, or 5th place, yeah, finishing 1st is different than finishing 2nd, but that's not what we're doing. We're saying I'm going to go select 5 people at one time. It doesn't matter what order you're selected. So I'm going to use a really simple example. Let's suppose I have 5 cars, okay? And the cars are car A, B, C, D, and E. You can make, Audi and Bentley, Cadillac. I don't know. I'm not that good with cars. Just make up whatever you want. And I have 2 very close friends. And I just won the lottery, so I have these 5 nice cars, and I'm going to give one to each one of my 2 best friends. So how many ways can I give these cars to my 2 best friends? Well, let's see. I can go, let's say the first friend and second friend, just to make it easy. So I can go AB. Now, what else can I do? I can go AC, AD, AE. I can go BA, BC, BD, BE. I can go CA, CB, CD, CE. I can go DA, DB, DC, DE, and I can go EA, EB, EC, ED. So the last choice, I give the 5th car to my first friend, and I give the 4th car to my second friend. Great. Now, right before I was trying to give my cars away, it turns out my second friend unfriended me. They're done. They took me off their cell phone, their email, everything. So I still want to give away the 2 cars, but now I'm going to give them to my true friend, my number 1 friend, because now I only have 1 friend. So does that change things? Well, a little bit, because right here and right here, those are actually the same thing. I gave car A and B, or I gave car B and A. I gave the same 2 cars away. So now that I'm giving them to my 1 friend, the order that I'm giving them can't matter because I'm still giving them the same 2 cars. Before, no, friend 1 got A, friend 2 got B. That's different than friend 1 getting B and friend 2 getting A. So I have some double counts here. In fact, if I have A, B, A, C, A, D, A, E, then this has been double counted. 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 So this has been double counted. 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 Oh my goodness, look what I did. I just crossed off half of the choices. Originally, I have, from the 5 cars, I'm giving 2 of them away to friends. So the original calculation was actually permutation 5 choose 2, which we know is 10. All right, excuse me, 20, 5 times 4. But the second calculation, I double counted. In other words, if I select 2 cars and now I put those 2 cars in order, there's exactly 2 factorial ways of doing that. I did 2 cars rather than 3. Because if I had done 3 cars, there would have been 60 choices here, and that would have just taken too long. So what I did was I took this answer and I essentially divided it by 2 factorial. Now, factorial is important because that's how many ways I can order 2 things. If I had 10 cars and I gave 6 of them away, well, 6 factorial is really large. That becomes a huge calculation. But in this sense here, since order no longer matters, that's a different type of calculation. That's what a combination is. And so the formula for a combination, which is really simple. So some people write it this way: combination n choose r, the same n and r as before. N distinct objects, I'm selecting r of them where r is less than or equal to n, is equal to the permutation of n choose r. But if I select r objects and I put them in order, then I'm going to overcount that exactly r factorial times, because there's exactly r factorial ways of putting r objects in order. So this is a very, very powerful relationship here between these two. And so with that said, the formula for combination, which most of us are very familiar with because that's the one we've used in many, many classes. And so we use different notation. The universal notation for this is, as you've all seen, this. This is not a quotient. We say n choose r. And the reason we completely change the notation is just to make it less confusing with permutation. I don't want it to look like permutation. So the permutation was n factorial n minus r factorial. But the combination means I have to also divide by r factorial, because that's the number of ways of arranging r objects. Another way of thinking about this is, if let's say the basketball team, okay? I grabbed 5 people at one time. I would use this calculation. But if I said, now I want to put those 5 people in order, I would now multiply my calculation by 5 factorial. And then that would put me right back to permutation. So this is probably the most common formula that we use in combinatorics, is the combination formula. And it's a really, really easy formula to use. But you do want to use your calculator. You don't actually need to show the individual factorials, because again, some of the individual factorials can be too large to conveniently calculate. So one of the first areas people love to use this are things like lotteries. Okay, so I'm going to go backwards. Think of a bingo card. With anybody who's ever played bingo, right? You have a bingo card. So you have a whole bunch of numbers. Let's just keep it simple. Let's just say it's numbers. All right, you have a whole bunch of numbers, and however many numbers you have, 10 numbers, 1,000 numbers, doesn't matter. And you're going to select a certain number of them. Now, how many ways can you actually do your selection? Well, a lottery, or the lotto things, it's actually the same thing. From a set bunch of numbers, you're going to choose some of them, but the order you choose them isn't important. You see, if I said, let's suppose I chose this number, this number, this number, this number, and this number. You see the result of my selections. What you don't see is the order I chose them. Well, what if I picked that one first, that one second, that one third, that one fourth, and that one fifth? Is that a different selection? No, it's the same selection. I am saying, what numbers am I going to choose? The order I choose them is irrelevant, because all I'm ever going to see is the final choice, not the order I made them. So anytime there's a lottery, it actually is a combination. Now, I remember I was alive back when California started the lottery, and it was very, very interesting because, you know, it was very, very political. And one of the things they conned people into, they said, oh, we're going to take all of this money generated by the lottery and we're going to put it towards schools and police and fire departments and all this. And everyone's like, yeah. What they didn't tell you was, all the money that normally went to those was now going to go somewhere else. They were just simply replacing where the money came from, and significantly less money as a result then went to those places, because not everybody plays the lottery. But having said that, in the early days of the California lottery, I do remember this because people would think they had a way of winning, and they thought they had a good chance in the original days of the lottery. And I don't know if it's still true, by the way. It was from 49 numbers, you selected 6. That was the original days. Again, that I don't know what it is today because I don't pay that much attention to it. But this was exactly how many ways you could fill out a lottery card, the lotto. And in fact, it was actually called Lotto 649. That was the name that they generically had. And over the years, I know they played with it and they've tried, messed around with maybe increasing the number of choices or how many you had to do. But if I said, how many lottery cards, how many ways could you fill out a lottery card? You just simply enter, 49, choose 6 on your calculator. And the number is, well, large. This is 13,983,816, almost 14 million different ways you could fill out a lottery card. Now, what was interesting though, in the early days of the lottery, I think they did it once a week, and they'd actually have a TV show with all the ping pong balls with the numbers, and they'd be drawing them out and then writing them down. In the early days, there were winners pretty much every single week. You say, what, if there's 14 million? Yeah, because there's a lot of Californians and 10 to 20 million Californians would actually play the lottery every single week. So it was not unusual that not only did they have winners every week, but they might have multiple winners every week. Okay, if you guys have ever seen the movie Bruce Almighty, just say, have you guys ever seen that movie? Yell it out.
Yeah. Yes.
Yeah, that's where he gets to play God for a week or something, and so he grants everybody their whatever prayers they had, and a lot of people say, I want to win the lottery. So it was like 1 million people won the lottery, and they each got like $11. That's a very funny scene. That's kind of what happened. People weren't getting very much money, but over time, as less and less people played, what you found was you'd hear it went weeks and sometimes months between winners. And so people would always have this idea, somebody's got to win. No, it starts over every time. It's sort of like when I'm flipping a coin, I just flipped a tail. Oh, well, it's got to go heads. No, it doesn't. It will eventually be a heads, but it doesn't have to do anything. The coin doesn't have memory. There's no chip in there that says, oh, I got to lean this way now. No, it starts over each time you do it. So if this is it, then what if I changed one of these? And I know that in the early days, they talked about changing it because there actually were too many winners. One of the first things they decided was, well, what if we went to 7? You have to get 7 right. By the way, I'm pretty sure they didn't do that, because if I have to get 7 numbers, then 49 choose 7 is now, what is this? Hold on. 85,900,584, and they realized, that jump is a little bit too big. Okay, and we might go a really long time without a winner. So I know they've tweaked it in other ways, but this is just an interesting starting example. You can't write down all the choices. Now, a number of years ago, I can't tell you what year it was. I just thought it was very interesting. I believe, somebody correct me if I'm wrong, I believe it was the Florida State Lottery. These computer nerds figured out a way to generate every possible number, and they actually played every number. I don't know how you could do that in a short, finite amount of time, because the jackpot was so big. You see, the jackpot rolls over. So the jackpot might be hundreds of millions of dollars. So they figured out a way to generate every number, the millions of numbers, and actually purchase, which guaranteed them they were going to win. They had to spend millions to make millions. And I just found it to be amazing that you could actually do that. I mean, it's one thing to generate all the numbers. It's another thing to physically go out and purchase them. I don't know if they hired a bunch of people. It was an interesting concept. I don't know if it's a wise concept. But technically, if you could generate all the numbers this week, you could buy all the tickets before the end of the week, and one of them's got to be a winner. Now, another area people love to use this is with playing cards. Okay. Now, I am not a gambler, but I do teach gambling on TV. No, I love teaching gambling as a means of showing combinatorics, because it's easy to do calculations when you're talking about coin flips or dice rolls or cards. Now, in a standard deck of 52 cards, let's say you're a poker player, okay? So if you're a poker player, there's 5 cards. So you have 52 cards. All right, now what are your cards? Well, your cards are a 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, Ace. And the ace can be at either end. And then you have suits. You have suits, and your suits are the spades, diamonds, hearts, clubs. So from these 13, call them number choices, there's also 4 suits. So that's your 52 cards. So if I just randomly said, okay, I'm going to shuffle the cards and you're going to select 5, or I'm going to distribute 5 cards to you. Well, clearly I can't have the same card twice. Now, anybody who's ever played cards, I don't care if you're playing Go Fish, when you receive your cards, don't you rearrange them in your hand? We used to play, I can never remember if it's gin or if it's rummy or if it's gin rummy. It's one where you had either like 10 or 11 cards and you're looking for straights and multiples. And well, you have too many cards in your hand. So you're going to rearrange them within your hand so that, oh, okay, I have a 3, 4, 5. And over here I have, 3 queens. Once you receive your cards, you rearrange them in your hand. That doesn't make it a different set of cards. So when you have cards in your hand, the order cannot matter. So that's why any calculation with cards generally is thought of as a combination, because the order cannot matter. So first of all, if I said, how many ways? How many ways can you have 5 cards? How many ways can you have 5 cards? Well, clearly that would be 52 choose 5, which would be 2,598,960, I believe. I know I've done this so many tens of thousands of times. There's about 2.6 million ways you can receive 5 cards. Yikes. So if you're the poker player, then what you're looking for are certain combinations, or that's probably the wrong word, certain sets of numbers or suits that would be beneficial. So without teaching you how to play poker, there are things that are better than others. For example, if I had 3 of the same kind of card, I have 3 kings, or if I had 3, 4, 5, 6, 7 all in a row, or if I had 5 cards that were all spades, these would be very, very good hands. Now, one of the things that I always found interesting when people are arguing, so a couple of us we're playing, and Joseph and I are playing cards, and I've got a straight. That's when 5 are in a row. And Joseph has a flush. That's when they're all the same suit. And we're arguing over who has the better hand. How in the world do we make that conclusion? Do I just memorize some random sequence of orderings? Or does anybody know how is it determined which set of cards is superior to another set from a gambling standpoint? In other words, who would win? Does anybody know? It's actually very simple. How do I determine if my 5 cards are better than your 5 cards? Anyone want to try that one? Think value. What makes it more valuable?
It's less likely to come up, maybe.
Good. The more rare it is, the more valuable it is. Okay. So for example, if I gave you 5 cards and you had 2 of the same number, that's called a pair. There's well over 1 million ways that you could have a pair. So it's not very valuable, but to have 3 cards of the same number, now that would be far more valuable. So let's calculate. And by the way, that's called a 3 of a kind. So if I wanted to calculate how many 3 of a kinds are there, so how many 3 of a kind. Now, what would a typical 3 of a kind look like? Well, a 3 of a kind might look something like this. Let's say 6s. So I have a 6 of spades, a 6 of hearts, a 6 of clubs, an ace of clubs, and maybe a 7 of spades. Okay, that would be a typical 3 of a kind. 3 of the same number, then 2 other numbers that are random and different from each other. If these 2 numbers were the same and I had 3, that's actually really, really good. Does anyone know what that one's called? If these 2 are the same number with these 3?
Is that a full house?
That's called a full house. Yeah, that's really, really valuable. I don't want that one. I want this one. So how do I calculate this? Well, it's real simple. First, we determine, I need to figure out which of these 13 I'm going to choose as my 3 numbers in a row. So to choose my 3 numbers in a row, I have 13, I need to choose 1. There, I have now selected which number. Now I need to pick 2 cards at random from the remaining 48, because I got to make sure that neither one of these is the same as this one. Well, how do I do that? I need to pick, then the first thing I need to do is pick 2 different numbers from the remaining 12 numbers. 2 different numbers from the remaining 12. So I've selected the number and now I pick the two remaining numbers. Now I have my numbers. Oh, I have a 6, a 6, a 6, an ace, and a 7. Now I need to select the suits. Okay, so let's go back to this guy. I've selected my 3 numbers, but I could have picked this, 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 this. Okay, there's a bunch of ways I could have picked my 3 suits. From the 4 suits, I needed to choose 3 of them. That's 4, choose 3, because the order I selected them was not important, only the result of my selection. Now, my 2 remaining numbers, one of them was an ace, but it could have been an ace of hearts. It could have been an ace of diamonds. I need to pick the suit. And I need to pick the suit. So if I said how many 3 of a kinds are there in a deck of cards, there's exactly this many. This is the number of ways I can choose my first number, the number of ways I can choose my remaining 2 numbers, and these are the suits. So when I do this calculation, there's 54,912 ways I can have a 3 of a kind. You'd say, well, that's really common. Well, I said there's over 1 million ways for a 2 of a kind. So it's not rare, but it's not extremely common. Remember, this is over 52 choose 5. So if I said, what's the probability? Oh, now probability would be this value divided by 52 choose 2. Or excuse me, 52 choose 5. So let me do that. Divided by 52 choose 5. And it's about 0.02. So I have about a 2% likelihood of having a 3 of a kind. That's not really common, but is it extremely rare? So for those of you who want to play cards, now I'll have people every single semester ask me for advice on gambling. I don't give advice on gambling. I don't gamble. I know the mathematics of gambling. That's why I don't gamble. You can't win in the long run. You know, it might be fun. I've played blackjack at Vegas before at a $2 table, you know. But I don't lose big. I won't win big because I'm only playing with $2 at a time. I don't even know if that's a thing anymore. No, I'm not a gambler, but I know the mathematics involved. So if I was asking what would really be a rare hand, well, it turns out the rarest hand you can have is a combination of things. The rarest hand you could have would be, first of all, I have a straight, which like 2 through 6 or 3 through 7, or technically it could be ace through 5. All the way down to 10 through ace. 5 in a row, again, you're rearranging them in your hands. If I have 5 in a row, that's called a straight. If I gave you 5 cards and they were all spades or all diamonds or all hearts or all clubs, that's called a flush. So it turns out the rarest hand there is something called a straight flush. That means I have all 5 of the same suit and they're in a row. So exactly how many ways could I do that? Well, if I put the ace at this end, then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 straights. There's only 10 different possibilities of the ordering of the numbers for a straight. Now, a straight, all the suits are different. So I have 10 ways to have the ordering of a straight, and then I have 4 choices for the suit. There are exactly 40 out of 2.6 million that are straight flushes. So here's the thing. So I'm a card counter. I'm a cheater. I've got, you know, like if you've seen the Solo movie, I've got the little thing in my sleeve that, you know, shoots the cards out so I can quickly get one in my hand. I've perfected the art of cheating at cards, and I'm going to show up at my table. And AJ shows up at his table. He's also perfected the art of cheating at cards. So we're both playing at our card table. We have the big stacks of chips in front of us, and we both have straight flushes. So who wins? Well, first of all, we go with the highest straight. The highest straight would be these. Do you guys know there's a name for that straight? Does anybody know what it is?
It's called a royal flush.
Nope. No, you're half right. It's called a royal
Straight.
straight. Okay, it's called a royal straight. So if I have a royal straight, I beat any other straights. But we both have straight flushes. Oh, so now we have the royal straight and they're all the same, that's called a royal flush. But there's still 4 of those, aren't there? Oh my gosh. So if you're going to cheat big, which, by the way, of the 2.6 million poker hands, they can actually be ranked from first to last. Is there an absolute ultimate highest you could possibly get? Does anybody know? So you said it. It's a royal flush, but which one? See, if you're going to cheat big. Don't have a royal flush and still not win. See, so I have my cards and AJ has his cards, and we both have royal flushes, but only one of us can win because the suits are also ranked. Does anybody know what the highest one is? Spades. So I have 10, Jack, Queen, King, Ace, and they're all of spades. That is number one. So if you're going to gamble, if you're going to be a poker player, that's the one you want to make sure that you have when you're sitting at the table. The royal flush spades high. There's only 40 royal straights, and those 40 are still ranked by the order here and then the order here. Isn't that crazy? Now, does it ever happen that somebody's sitting at a card table and has that? You know, I don't know. I don't know if that ever happens. And I would be highly suspicious if I was sitting at a card table and somebody had, royal flush, and they're just randomly dealt cards. I'm wanting to check their sleeve at that point. But so cards are a lot of fun because the calculations are not complicated, but you wouldn't write down all the choices. That'd be just nuts. So let's do some more practical problems. All right, so here's what we're going to do. We're going to form committees. Well, let's keep this really simple. This is one of my favorite ones, is when you talk about how many ways can you form a committee. So let me just throw some simple numbers at you. All right. So there are 40 students in the class. And let's say, let's keep it simple. Let's say 24 are women and 16 are men. I don't want the numbers to be the same. Actually, I don't know how many. I'm just making it up at that point. Now, I want to form a committee. All right. I want to form a committee that maybe, we're gonna do all sorts of planning. Maybe our committee is for, future party planning or math contest planning, whatever, we're going to form a committee. So first of all, here's the first question. How many 5-person committees are there? How many different 5-person committees could be formed? And 40 students, I'm going to choose 5 people. So how many ways? I don't want a number. Tell me what is it? It's a permutation, a combination, it's a factorial.
Combination.
And what would the numbers be that I use?
40 choose 5.
Perfect. 40 choose 5. This is exactly how many 5-person committees we could form. So 40 choose 5. That's large. 658,008 people. That's how many. Wow. Now, what if we had a situation where you said, well, I don't want a 5-person committee that's all 5 men. I don't want a 5-person committee that's all 5 women. I kind of want committees with both. Oh, so how many committees of each mix could we have? That's the next thing I want to look at. So how many with, I'll just say each mix of women and men. So what would the mixes be? Well, let's see. I could have, let's do women followed by men just to keep it. So I could have 0 women and 5 men, 1 woman and 4 men, all the way up to 5 women and 0 men. So how many different categories is that? 0 women up to 5 women, that would be 6 different categories. So let's do that. So I'm going to have 0, 5. I can have 1 and 4. I can have 2 and 3. I can have 3 and 2. I can have 4 and 1. I can have 5 and 0. These are the possibilities. So let's write down the numbers. So how many ways can I have 0 women? Well, that would be 24 choose 0. Obviously, that's 1. How many ways could I have 5 men? That'd be 16 choose 5. And I am matching them, so I have to multiply these. See, if I just said how many ways can I have a certain number of men, but I'm matching it with the same certain number of women. Here, this would be 24 choose 1 and 16 choose 4. So you can kind of figure out there's a pattern here. I've written probably too tight. And the last one, squeeze it in here. There we go. So let me do the calculations for each one. So in the first case, this would be 4,368. Now in the second case, again, any cheap calculator, this is easy to do. 43,680. In the next case, my fat fingers, try that again, 24. That's big, it's 154,560. That's even bigger, 242,880. $170,016, and then the last one, 42,504. Now, none of these calculations are taxing, none of them are difficult. If I add these numbers up, it has to add up to this because I've just listed every possibility. So here's how we're going to do it. Everybody's going to put their name down on a piece of paper. We're going to fold the pieces of paper up. We're going to put them in a bag. We're going to mix them all around. And then I'm going to have Cynthia come up and she's going to grab 5. And this would be without replacement because we don't want the same person twice. That wouldn't be a 5-person committee if one person could be selected twice. So she's going to take the 5 names out. Clearly, the order does not matter. You're either on the committee or you're not on the committee. Okay. So here's the question. Now I'm going to have Cynthia choose 5 names, and I want to find the probability the committee has at least 3 women. Okay, that's the question. I want to find the probability that the committee has at least 3 women. Well, how would I do that? I'd find all the committees that have 3 women or more on them, which would be 3 or more women would be this, this, or this. I would add those up over this denominator. So let's do that. Just right now. So it'd be 242,880 plus 170,16 plus 42,504 over 658,008. That would be the answer. So let's go ahead and do that. And we see that that's about 6,9. Remember, I said 4 decimals is kind of the universal norm for probability. If I could reduce this fraction, that would be great. But I have an astronomical denominator. So even though I could reduce it, it would still be astronomical numbers in numerator and denominator. And that's not entirely useful. So almost 70% of all of the committee choices that I could do would be 3 or more women. That's interesting. Now, question, could I have done 3 or more men and still got the same answer? Answer that for me. Could I have done 3 or more men, which are these 3, and still got the same answer somehow or another? I misread the question. I did the calculation for 3 or more men, and then I went, oh, you wanted 3 or more women. Do I have to start over or can I answer the question? Anybody want to tackle that one? What is the answer for 3 or more men? That's these guys. Is it that?
No.
What would it be? This is actually really simple. What's the complement of 3 or
1
more?
minus the
1 minus.
yeah.
That's it. Because this is the complement. Oh, I did this calculation. What if I had accidentally done the complement? Or what if I intentionally did the complement? Then I would take my result and subtract it from 1. So the result for this would just be 1 minus this. Now, why is that important? Because the nature of the question. So now let me change the question on you, because this is how it works. All right, I'm going to form 5 committees at random. What's the probability that I have at least 1 woman on every committee? At least 1 woman would be this plus this plus this plus this plus this over this. That's a lot more calculating. Well, what should I do if I said at least 1 woman? Take this and subtract it from the whole, because this is the complement. And remember I said before, if the complement is easier to calculate than what you're being asked, then do the complement and then just subtract it from the whole. If it's how many committees, I do this and subtract it from this number. If it's probability, I do this over this number and subtract that from 1. It's the same concept. So calculating complements is still very, very useful if the complement is simpler than what you're being asked. Okay, that's really important that I see that. If it's simpler than what you're being asked. I asked a calculation that was exactly half the calculations. So complement wouldn't have made any difference in this case. But had I asked a calculation that was more than half, then I probably would have gone with the complement as being a more efficient way of doing things. Okay. So these are really simple ways of using combinations to answer questions. Now, a lot of folks, when it comes to combination and permutation, obviously get them confused because both of them are very similar. Both of them are quotients with the same numerator, and part of the denominator certainly is the same. Both of them have an n factorial in the numerator and both have an n minus r factorial in the denominator. It's very easy to get them confused. So how do you know the difference? And by the way, this is a simple conceptual idea. Don't think definition so much as practicality. If I'm doing a calculation and I know it's either a permutation or a combination, how do I determine which one it is? A simple litmus test most people use is something like this. If I rearrange my choices, if I rearrange it, is it a different answer or is it the same answer? If I'm selecting my lottery numbers or I have the cards in a deck of cards, if I rearrange them, is it still the same cards in my hand? Yeah, then you know it's a combination. I'm selecting, first, second, and third place of a road race. If I rearrange those, is that a different outcome? Yeah, being first is different from being second. That would be a permutation then. Okay, that's a really, really simple way to start. If changing the order of the outcome changes it or leaves it the same. Now, a simple historical way that I always teach people how to remember the difference of this, okay? Pizza. Think pizza for a moment. Now, you go to the pizza place, and it's early enough that I'm not worried about you getting hungry for lunch. I love pizza. You go to the pizza place and you tell the person, okay, start the pizza. I want you first to put on the pepperoni. Then you're going to put on the sausage. Then you're going to put on the black olives. Then you're going to put on the green bell peppers. That's my favorite, by the way. Okay. And so the person says, okay, I got to put them on in that order. You go, yep. If you don't put the olives on first, you put the olives on third, and you don't put the peppers on second, you put them on fourth. Now, when the person puts all the ingredients on the pizza and it melts and spreads out, the final results, they're all at the same level height-wise. The order you put the ingredients on, if you think about it logically, doesn't affect the outcome of the pizza. If I had put those same 4 elements on in any order, my final pizza is still going to look exactly the same because things melted and went sideways. So when asked, how many ways can I come up? So when you go to the pizza place and you see all the toppings and you say, I want 3 toppings. Think about it logically. Does it matter what order you ask for the toppings, or is the pizza going to come out the same? Yes. That is why when you get the pizza with everything on it, everybody knows this now mathematically. When you get the pizza with everything on it, it is not called a permutation pizza, is it? What's it called? What is that pizza called when you get the one with everything on it?
Combination.
Combination pizza. That's where the term comes from. It was a mathematician who invented pizza, I think. That's where it comes from. You think I'm joking? No, actually, that's perfect mathematics. It's a combination pizza, not a permutation pizza, because the order of the toppings does not matter. Only the choices. So I want to have certain numbers of choices. So let's construct a pizza. So we have a pizza place, and let's say they have two types of toppings. They have meat toppings and they have non-meat. We'll just call those veggie toppings. Okay. My wife gets spinach on pizza, which is it's just wrong. But anyway, let's say of the meat toppings, there are let's say 6 different meat toppings, and there are 10 different veggie toppings. And you want to get a 4-topping pizza. And you want at least, let's say, at least 2 meats. You're going to order a 4-topping pizza with at least 2 meats. I would like you to tell me exactly how many ways can that pizza be constructed. So I'm going to pause for a moment to give you a minute. You can do this on your own. Rebecca thinks she's got a viable answer. So first of all, what are my combinations of meat and veggie? What are my choices here? At least 2 meats.
We have 5 different ways we can make the pizza with like 0 meat and 4 veggie toppings.
Okay.
1 meat and 3 veggie toppings, and then 2 and 2, 3 and 1, and 4 and 0. I just wrote them out just to.
Okay, so that's perfect. This is exactly what we need to start with. Now, are the first 2 calculations you mentioned, the 0, 4 and the 1 and 3, are those useful? Yeah, there's less calculations. I might actually choose to go that route. That would be the complement route, wouldn't it? Now, how many ways can I do this one?
It's 6 choose 2 times 10 choose 2.
Good, times. Common mistake is people will add these. You're matching these, and now I'm going to add it to my next thing, which would be, keep going.
6 choose 3 times 10 choose 1. And then 6 choose 4 times 10 choose 0.
Beautiful. That's perfect. Absolutely perfect. That's exactly what you're going to do. So now when we calculate these, I'm less concerned with the final answer, because the final answer just means I hit all the right buttons on my calculator. But that's not useful if I don't have the right things to hit in the first place. And then the last one, 6 choose 4. And you said that was 890?
If I hit the buttons correctly.
I believe you are correct. Now, how else could I have done this? Because you said there were 5 different ways that I could put meats with, the numbers of meats with the number of veggies. There was a 0 and 4 and a 1 and 3. If I had chose that route, that would have been a little bit less calculation. So I could have done that, but then what would I have done if I did that route? Let's talk about that route. I went the other route. I did the 6 choose 0, 10 choose 4, plus 6 choose 1, 10 choose 3. This would be the route of less than 2 meats. But what do I do with this number? In other words, how do I get that answer? Well, exactly how many 4 pizza toppings are there, by the way? Exactly how many 4 pizza toppings are there? That's a fairly easy one. Anybody want to try that one? How many 4 pizza toppings are there? I'm going to pin myself again.
Just 16 choose 4.
16 choose 4. 16 choose 4 is the number of 4 pizza toppings. These are all the toppings that have less than 2 meats. All pizzas, the ones that have less than 2 meats, and I would subtract them. And this should give me the same 890. Now, you notice I put parentheses around this because I got to distribute the negative correctly. So let's do this calculation just to be sure. So right here, I'll write it in, because again, there's the nice thing about these types of problems, there's multiple ways to check that you did it right. So 10 choose 4 times 6 choose 0, that would be 210. 10 choose 3 times 6 choose 1, that would be 720. And 16 choose 4, this would be 1820. So if I said 1820 minus this sum, the sum of 210 and 720, oops, and 720, there we go. And I hit my handy dandy calculator and it says 890. Right? It would not have mattered if I did it this way or I did it this way. I get the same answer because I'm looking at the problem correctly, but from 2 points of view. You can always do things using the complement. You can always do things direct calculation. You make the choice on which you think is going to be less taxing. You say, oh, there were less calculations if I did the complement. Are there less calculations? You only had 2 sets here, but you still had to do that. And then you had to subtract from the total. So you might argue that, you know, the complement was just busy enough that I think direct would probably have been a little less challenging. It would not have mattered. You got the same thing. That's the main thing. Okay, so this is what I wanted to get through today. This is, again, the most common type of problem. So in the textbook, there are just brilliant examples, tremendous number of great questions in the homework. You want to practice it till you get it really comfortable, because the next thing, one of the next things we're going to look at, we've got n distinct objects. We're going to choose r of them. And all my choices have to be different. What if I said from n objects, you're going to choose r, but you could repeat? So what do you mean? How could you do that? You're going to the ice cream parlor and you're going to get a cone with 3 scoops on it. And maybe they've got, 40 different flavors. And you've decided I want 3 different flavors. Great. So you have a 40 choose 3. But what if you wanted the same flavor 3 times? What if you wanted 2 of your 3 flavors to be the same flavor? What if you allowed for the same flavor more than once? That calculation is significantly more complicated. So we're doing the combination where each choice has to be different. What if we allow for repetition? In other words, that's the next major formula we're going to derive, which means we've got to get this one down. We've got to get this one down, absolutely set, before we can do the next one. All right. So as always, let's take a short break.